Hello, my name is Askeland. This is my sixth video about Riemann's hypothesis. In this video, I'm going to calculate the standard deviation between convergent zeros and analytic zeros using the Euler product and the oscillating condition from my Riemann hypothesis proof. What you see is a calculation and recalculation of Riemann zeros in the lower plot as the length n of the zeta sum increases. A Riemann zero occurs as a green spike in the lower plot. On the right-hand side, I calculate the standard deviation between my zeros and analytic zeros of established theory. According to my Riemann hypothesis proof, the standard deviation should be smaller as n increases. As you see, this is the result. I will explain the details of this visualization in this video. A convergent zero means that the zeta sum formula for specific n values can be factorized with Riemann's zeros, and that you will find the zeros from the Euler product. This video demonstrates numerically that these zeros become more accurate as the length of the sum formula increases. These calculations match the theory of my Riemann hypothesis proof. In order to understand this video, you need to study my Riemann hypothesis proof in video number 1. The condition which solves Riemann's hypothesis occurs already in equation 11. Large g of 0 and small g of 0 are integrals and therefore limits of sums. Equation 11 can be changed to equation 35, which is a rotational condition. I show in video number 4 how equation 35 can be changed into the equation inside the green frame. Using n equals 9973 gives the following discrete solution around Riemann's first zero. When I enter these values into the phase diagram of the Euler product, I land on or very close to Riemann's blue analytic continuation, but only for discrete values. In video number 5, I show that I simply can take the derivative to find Riemann's zeros. Then Riemann's zeros occur as green spikes in the lower plot. In the calculations I use a prime p as the length of the zeta sum formula. This is the discrete distance between the arguments on the critical line. Here you can see how many zeros I have calculated. I compare the locations of these zeros with very accurate zeros calculated by Urlisko. Then I calculate the standard deviation between his values and mine. In this case, for n equals 9973, the standard deviation of the error is 0.092. The result is based on 52 zeros. I have shown in video 4 that the accuracy depends entirely on the distance between the arguments on the critical line. This distance is inversely proportional with the natural logarithm of the length of the zeta sum formula. Squaring n will cut delta b to 1/2. The standard deviation should then be cut to 1/2 when n goes from 10,000 to 10,000 squared equals 100 millions. We should then see a falling value of the standard deviation to almost 1/2 of 0.092. You will now see the plot of the standard deviation between convergent zeros and analytic zeros for n between 10,000 and 100 millions. As n increases, more zeros are used to calculate the standard deviation. Here you can see that the standard deviation is reduced to 1/2 when squaring the length of the zeta function from n equals 10,000 to 100 millions. I have in this video documented that the zeta function can be factorized with specific n values. I have documented that the zeros found from the phase diagram of the Euler product becomes more precise as the length of the zeta sum formula increases. The results are a confirmation of my Riemann hypothesis proof in video 1. Thank you for watching.